I'm Simon, as Jan's already said, talking about serverless WebSockets at scale today. And really the aim that we're going to try and answer the question, is AWS ready to provide serverless WebSockets at scale? But first, who am I? So I'm a principal software engineer at DAZN. I've been at DAZN for around 2 years now, with over 8 years experience. Most of those actually working with serverless, and so I guess together, love serverless, love WebSockets. I want to combine the two together. I want serverless WebSockets. Bit of background onto DAZN. It's a sports broadcaster, so think a little bit like Netflix, but for sport. So we show things like the Champions League in Germany, and we'll have millions of people watch those events online on their mobiles, TVs, laptops, wherever. So today we're going to cover through our requirements, so why we were looking at serverless WebSockets. We're going to go into some detail on AWS Appsync, some of the issues that we saw, some of the good things as well. Go into WebSockets for API Gateway, which is another offering, AWS IoT. And then we're going to go into some detail on our solution, what we've ended up with and our load tests around it, and then maybe give some insight into the future and what we're going to actually build in the coming years. So the feature that we were looking to build here was key moment. So we really wanted to show, as you can see in these screenshots, we wanted to give users the ability to kind of build their own highlights reel. So when a goal happens, or maybe a red card, a contentious referee decision, we want them to be able to just click on their scrub bar and go back and watch it again. And we wanted this to work for both live and catch-up events, so you can do it whenever you want. And the product requirements here are quite simple. So we support live events. Most of our viewers are live, and we want it so that when a viewer is watching live, they get a key moment within 30 seconds of it happening. And that's really important, because if you've just seen an amazing goal, you don't want to be able to watch it again. You just expect it to be there. So it has to be there very quickly. And we do also want to support catch-up events. People do still watch them. And also, imagine if you're a live user and you come in at halftime, you need to be able to see the historical events that have happened as well. And we translated these into some fairly simple system requirements. So translating the 30-second requirement, we thought, okay, let's publish updates to users rather than have them poll. And this is actually a really important thing for DAZN, because we're showing live video at the same time. And polling is relatively expensive. And because we run on TV devices where they really prioritize the panel over the CPU speed for obvious reasons, we're so restricted that if we're polling, we could cause stuttering on the live video. And if we do that, what's going to happen is that our feature is going to be turned off straight away. We're never going to be able to go live, and we're just stuck. So we wanted to publish. We want to be able to retrieve previous messages and subscribe to new ones. So that's to support both live, new messages coming in, and catch up. And we really need to perform with high traffic on a global scale. So we want reasonable latency, we want regional failover. We have a really reasonably unique problem in that millions of users come online just before a major sporting event kicks off. So we'll go from around 10, maybe 50,000 people online to a few million in a few minutes. It's pretty insane, and it leads to really bursty traffic, and it's actually quite hard to predict as well. Thank you for the police siren. So our requirements here are kind of translated into this diagram. We put a really, really high level view on this, and we thought DAZN services, like this new key moments thing, would want to publish updates. So it wants to say a goal happened in this match. It wants to send that to some service on AWS, hopefully doing all of the undifferentiated heavy lifting, as Werner always says. And then we want our millions of users here on the left to be able to request the historical data, so the key moments that have already happened, and subscribe to updates all at the same time. And then whenever updates come in, they get pushed those updates. So reasonably simple. And we'll come back to this diagram a few times. But why WebSockets? Why are WebSockets the good thing for pushing updates? So here's a reasonably simplified diagram of how a WebSocket works. They are quite simple. You make a HTTP call. The server says, excellent, I'm going to upgrade you to a WebSocket. And then you just, after that, you have a connection. You have a persistent TCP connection. And over that connection, you're able to send messages from the client to the server and the server to the client. So it's full duplex. This makes it far more versatile than the main web alternative to WebSockets, which is called server-sent events. So to send to the client. They also have some really strange limitations. For example, I think the default limit of the number of open connections you have is 5. And due to the way that we need to sync up both the stream and send new ones, we actually have 2 channels that we would want. If you had 3 tabs open, all of a sudden it breaks. And I've seen this happen on multiple websites before. It just silently breaks, you stop getting updates. Whereas WebSockets don't have these limitations. And all of this just results in a great UX. You can have this directional communication just happening all the time with no overhead, no headers, no cookies, everything's cool. And also, why serverless? Probably something that Jan's quite familiar with, something similar along these lines. So the blue bars here are our autoscale capacity if we were running an EC2 autoscaled or an ECS service. So to the left of the big spike, you've got redundant capacity because the red, which is our capacity requirements, is much lower. So we're basically wasting money. And then during a big game, the red spikes above the blue, which means that we're probably going to have increased latency, maybe downtime. And we're going to go, oh no, everything's broken. Let's scale up even further. And then we'll scale up. We maybe fix the issue just in time. And then all of our users disconnect. And all of a sudden we're wasting 80 or 90% of our capacity, wasting loads and loads of money. And we've had bad user experience as well with the increased latency. As a software developer, I want to focus on business logic. I do not want to be dealing with this scaling sort of thing. So being able to avoid thinking about those auto scaling rules whilst also having the cost per unit really easy to calculate in a serverless world, we will just follow the red line. It will follow it smoothly, our costs fall, and we don't have to think about this redundant capacity or difficulty in scaling. The one difficulty with scaling on serverless that we kind of have as a limitation on this is that we didn't want to be triggering lambdas all the time because of the limits on them. So after the initial burst capacity, we're limited to 500 new concurrent executions per minute. That's a very high limit for use cases, but when you think about lots and lots of people coming on all at the same time, we could quite easily hit that. It's a hard limit. So back to our high level overview, and we have AWS Appsync here. So it was one of the first products we saw when we were thinking, let's put a service in here. And the reasoning for that is how it's sold on its website, basically. So here are a few quotes from the product website. We've got, it's a serverless backend for mobile and enterprise applications. Excellent, we want this to work for mobile and web. It uses GraphQL. We weren't specifically looking for GraphQL, but it's something that is kind of like an added bonus, a bit of a perk. It's got the unlimited throughput and storage that scales according to your business needs. Well, virtually unlimited sounds a bit scary. Is it unlimited or not? But it's much better than limited. And the real important bit for us is that it enables real-time subscriptions across millions of devices. That's exactly what we're looking for. That's exactly why we're looking for a solution here. This bit's hard. So it's basically flexible, serverless, scalable, real-time GraphQL. It's got everything, and it's just what we wanted. So we jumped in. And one of the first that we saw was GraphQL is really powerful. It might sound obvious to some people here, but it was the first time that I'd actually used it in a real business application. Here's how we kind of modeled our data. We were like, okay, we have a fixture, otherwise known as a match. And then we have key moments, which can be attached to them, which just have a type like goal, red card, or penalty. And then they have associated with them as well. So it kind of just fits now. And from here, you can see how these relations might grow and might have, from fixture, you might have competitions and tournaments and all sorts attached to it. So it's great for APIs with complex data structures. The fully serverless nature of it as well is absolutely brilliant. When you come with a serverless database such as Dynamo, it just works. And it's got a full feature set. You can build an entire application centered on Appsync. And if you see Jan's masterclass on building a social network, you will see a real example. It does work. And of course, the WebSockets part works as well. But we really had some pretty major hurdles along the way that actually turned into blockers. The first one that we saw was authentication. So because of the scaling limits that I mentioned earlier with Lambda, the 500 new concurrent executions per minute, we had to use an out-of-the-box scaling method. So we didn't want to use a custom authorizer. We thought, okay, here's our setup for authentication. We have backend services on the right here. We want them to authenticate with IAM. It's kind of the de facto standard for AWS to AWS. But our users, we don't really care about. We obviously don't want them to be able to publish any messages. They're just reading data, and it's not sensitive in any way, shape, or form. So they can just have a simple API key or anything at all, really. Unfortunately, at the time, AWS only supported a single authentication method out of the box. So we were forced to use the lowest common denominator. We couldn't ask our front-end clients to use IAM, so we had to have both using an API key. And there are other limitations here as well. We couldn't have it, you can't have per API key permissions. So we had to hard code in our GraphQL resolvers the fact that the API key for our services is the only one that's able to publish and send mutations, whereas the front-end users can read. So it's not really living up to security best practices such as mutation. This has now been fixed, which is brilliant. We gave that for AWS pretty quickly. I think since November 2019, we've been able to have multiple auth methods. But one of the other major ones was the fact that you have to query and subscribe. Now, this isn't specific to Appsync. This is actually more of a GraphQL problem. And here's a process diagram that basically shows what a client has to do to both get the historical data and to subscribe to updates. So first of all, they're making a call to Appsync's HTTP API or GraphQL API to say, I want to subscribe. It's responding with a WebSocket URL, something that you can actually do. Then you can open the WebSocket with it. Then you can subscribe to the topic that you want. So that's just a simple message over the WebSocket. And only after all of that's happened can you query data to get the existing key moments. And then, of course, Appsync will respond with them. So it's not totally unreasonable, but it is a fair amount of front-end logic. It's making 2 requests to Appsync itself and opening a WebSocket. And one of the really important things here is that because the connection to the real-time data is separate from the query, you have a potential race condition. So what we've had to make sure here is that the subscription must happen before the query, because if you query before the subscription, you could have the new broadcasted message come in the meantime and you miss it. And of course, that's terrible. If you miss a critical goal because you've just opened the event at just the wrong time, it's not something that and we'll come back to why those race conditions are important as well when we talk about caching. Next one is global deployment. So DAZN is global. Got a global launch coming in December as well. So we want multi-region, do something like. So we use Route 50 licensing. We have sync running in 3 regions, and we just route based on whichever region is closest to the user, basically. Now, because of the fact that the query and subscribe are doing 2 different API calls, they could technically be served by different regions. This is incredibly highly unlikely because of DNS caching. But at our scale, we have to kind of account for the fact that unlikely will probably happen to a decent number of users. And one of the really difficult things with that is that if one of the Appsyncs has received the mutation and one of them hasn't yet, then again, you have a race condition, you can potentially be missing data. So we'd have to be publishing to all of them, making sure that it's all in sync, and it just felt a bit dodgy. Now, caching. caching was tough. So each user on Appsync performs a query on connection. So they're saying, what are the existing key moments? One Appsync query is one Dynamo query. That's easy setup for us. We've got a native resolver that just says, when someone requests this, query this data. We had a limit though of 3,000 read units per second per partition, which for almost all use cases that I can think of is loads. It's absolutely plenty for most people, but for our world, that means a limit of 3,000 new users connecting per second per fixture or match. And when you actually calculate that out, it will take, if there's 1 million users trying to come online, it will take at least 5 minutes to fetch all of the data for a single match. And in the meantime, they're having to retry, they're getting errors, everything's breaking for them basically. So not a good user experience when we want to be providing our best user experience. So we were thinking, okay, maybe we can do something better with changing partition keys, caching, of course, and changing to Dynamo on demand helps a little bit with the scaling, but it still has that same hard limit. So I thought, okay, let's cache. CloudFront, easy, put CloudFront in front of it. We explored that, but it very quickly falls apart because of the fact that you have your query and subscribe race condition problem. If you had the query cached, say, a minute ago, and you've subscribed, but a key moment's happened in the meantime, you missed that key moment totally. And it would happen frequently if you were caching with CloudFront. So too many race conditions, it's out of the question. What about DynamoDB Accelerator? You can just put that on top of DynamoDB, it adds caching, right? Well, unfortunately, Appsync has no native support for DAX or DynamoDB Accelerator, and DAX doesn't really support any sort of advanced invalidations on individual queries. It only supports them on items. So we'd have to remodel our data, which is something that we weren't really that keen on doing. So no. What about Elasticache? So can we actually just cache it in any other cache whatsoever? Well, no native support, but we could use a Lambda. So we could add a Lambda in front and say, I'm going to query it from Elasticache, and that's the same for any cache at all. But because of the Lambda scaling limits, we didn't want to do that. So we found that one does not simply cache Appsync. And we contacted AWS and we're like, what on earth can we do? And this was the best thing that we could come up with. We'd duplicate the data n times when writing it to Dynamo. So let's say n is 10. We'd copy the data 10 times and basically hope that it would go on to different partitions. Luckily, DynamoDB on demand is good enough to repartition your data when it needs to anyway. And when the front end's querying, it can select a random number between 1 and n and say, okay, I'm going to query from this partition. And that works. It resolves the query load. If we had 10, we'd go from 3,000 to 30,000, which is pretty extremely high. But then we're looking at increased costs, higher latency, and no single source of truth. To be honest, I think that this data is highly cacheable. You just need a good invalidation system. Being able to have that many read units coming into Dynamo is going to add up at our scale. It's going to cost probably thousands. So the complexity here was just no. So we decided to run away from it and basically give up Appsync. However, since we did our investigations, Appsync does now have caching, and it's good. That was released in November 2019 as well. And you can use Elasticache, Redis, or Memcache, which is great, reasonably cost effective, really high scale. But unfortunately, it doesn't support invalidations at all. So when the data changes, it will just stay there as stale until the TTL expires, which is something that we can't deal with because it just leaves us with exactly the same race conditions as before. We can't have it so that a user will miss the broadcasted message. So we came back to a high level diagram and we were like, okay, there must be something to put in here. We must be able to find a different service. And we're keeping our eyes open. And then reInvent 2018 happened and there was an announcement for WebSockets for API Gateway. We're like, ooh, this sounds good. So let's look at how this one's sold. So historically, building WebSocket APIs required setting up fleets of hosts. Yeah, it's difficult. And they were responsible for managing persistent connections that underlie the WebSocket protocol. Yep, That's the most difficult part of WebSockets, is they're persistent and you have to have a lot of hosts because you have, basically it's not easy to load balance as well. Now with API Gateway, this is no longer necessary. API Gateway handles the connection between the client and the service, and it lets you build your business logic using HTTP-based backends like Lambda, Kinesis, or any other endpoint. So what it's actually claiming here, and what it does, is that it's converting WebSockets, which are operationally complex, to a traditional model. So it's giving you HTTP service calls, which is key moments, post a key moment to AWS, and AWS says, okay, I'll broadcast this to the millions of users. So like, yes, it's brilliant, sounds perfect. And we immediately started evaluating it. Well, it's flexible. You get access to send messages to each individual connection. So on that, you really get some versatility and more control than Appsync. Appsync is a much higher level solution, whereas WebSockets for API Gateway kind of sits at a lower level. It's a bit more flexible there. It's fully serverless. You can choose to use a Lambda for all actions like connections received, disconnected, message received, and then of course just broadcast by making a post API call. But not broadcast. It's only really sending messages to specific users. So it's not designed for broadcasting across a single message to millions of users, but it could deal with millions of connections being open. But for the broadcasting use case, you need to store each connection in DynamoDB. So you need to have connection ID, blah, and maybe what fixture they're watching. And then to be able to send messages to all of them, you need to make an API call to AWS for every single one of them. So if you had 1 million connections watching a single fixture, you have to query all of them out, put them maybe into some queuing system to deal with actually doing all of this, loop over all of them and make an API call. It's going to take a while. You're going to hit Lambda scaling limits just trying to do that all at once. And it's a lot of unnecessary database calls. It's actually quite expensive. And it's not something that we're willing to cope with. So that was over quickly. Not good for WebSockets for API Gateway for our use case, but huge potential for others. So back to the diagram again, and we put AWS IoT Core there. The reason for AWS IoT Core is that it actually powers Appsync's WebSocket situation, and it can support billions of devices with trillions of messages. So it's really, really high scale, easy to use services like Lambda, Kinesis, and S3. Nice. It supports HTTP WebSockets and MQTT. WebSockets are what we're after. It's got a pub/sub message broker, and that supports messaging patterns from one-to-one command and control, which is really what WebSockets for API Gateway is for, or 1 to 1 million or more broadcasts, which is exactly what we're looking for. Perfect. So again, evaluated that straight away. It's mature. It's been around for much longer than the other options. It's got loads of features, but unfortunately loads of them are irrelevant. Good monitoring, which is something that Appsync was totally missing. And then we immediately hit our cons again. We got authentication. And the limitation at the time was that MQTT over WebSockets, which is the one we're forced to use, only supports SIGV4. So we need AWS access key and credentials, which really the best way to do that is to use Cognito, which we didn't want to set up because it requires making more HTTP calls to get the Cognito creds. And it all just became a big mess and quite complex for us in our specific case. This is now also fixed because you can use custom authentication. So really nice. But unfortunately, at our scale, we need to use a Lambda authorizer. So we have the Lambda limits issue. So we just kind of go round and round in circles. So we moved on from IoT. We didn't want to model around it. And we thought maybe we should stop looking for a single service to do everything. Maybe we should put our own thing here that's cloud native, but not just one big managed service. It's called Pubby because naming things is hard. It publishes things to users. That's about it. So we designed our requirements here. Based on what we'd learned from earlier, is we wanted a single shared WebSocket connection for subscribing and querying the data. We wanted global scale with no race conditions. So using that shared WebSocket connection, we wanted to do everything. We wanted minimal operational overhead. So we wanted to be as close to serverless as possible. And maybe we could make it generic for use by other applications. So if we're putting all of this work in, why can't it basically be a platform service within the zone? So we immediately designed our architecture. On the right-hand side here, we've got the kind of complexity part. So we've got the way that we're getting all of these millions of users connected via WebSockets. So they're going through Route 53 latency-based routing to any of our regions. They hit a load balancer, where it comes through to an ECS service. So unfortunately not serverless at all. The WebSocket comes all the way through to those. Okay, subscribe to, and then it receives messages over Elasticache, Redis, PubSub, and can send all of those users messages whenever it receives an update. And then for broadcasting new data, we've got the architecture on the left, which is fully serverless. So you've got our services like Key Moments, making a post API call to an API gateway. And all that's doing is basically inserting some data into Dynamo for the historical lookup, and then using SNS to fan out to a multi-region approach. So we're able to say an update happened, and this publishing Lambda is triggered once for every region. It invalidates its local cache, and it says this actually changed, so it gets broadcasted. So somewhat complex, but reasonably simple, and a lot simpler than what we were expecting, but unfortunately not serverless. So that's it all together. And we immediately thought, okay, well, the real thing we need to test here is the load. Can this deal with the zone scale? So we did some load tests, and we thought, let's make EU Central 1 in the red here, hit capacity at 2 million users. We're going to do a load test of 3 million. So we're expecting US East 1 to take over and deal with the remaining connections. That happened. We were not happy at all. We had a total catastrophic failure, and we really weren't expecting that. We were expecting Route 53 latency routing to just detect that things were going badly and fail over. Turns out that's not the case. Latency routing doesn't do that at all. It's just the latency between the user and AWS, not the user and your service, nothing clever like that. However, Route 53 does support CloudWatch health checks, which are incredibly powerful. So now we can fail over whenever we want. So we implemented a few of these things based on the number of connections per task and CPU usage, and started proactively failing before the actual failure. And what that meant is that the next load test ran like this. So the slight shading is our comparison to expectations, where we weren't quite as good as the absolute perfect scenario. And that's because of DNS TTL. So you've got a 60-second TTL until the failover actually happens. It's not the best, but it's not the worst. We haven't got a total outage. It's just a slight delay in getting some users across. So conclusions, what have we actually learned, and is AWS ready to provide serverless WebSockets at scale? Well, Pubby deals with a specific use case. It's designed just for key moments, really, but we made it generic enough that it can be used for other teams at the zone. It is now being used by many other teams at the zone. It's highly available with seamless regional failover. It's got an uptime, I think, of over 5 nines. And the latency is 0.7 milliseconds compared to Appsync at 740 milliseconds on P90. So really fast, all over a single shared native WebSocket connection, but it's not serverless. Appsync, however, incredibly powerful, probably too powerful for something like Key Moments. It's much more of a whole application sort of thing. Subscriptions really are the weakest part, and that's all we really wanted it for. And these high-level managed services have their downsides, but definitely recommended for a more complex system with many related models, because that's where GraphQL comes into its own. WebSockets for API Gateway is a huge opportunity for WebSockets. The lack of broadcasting, though, is just not good enough for us. But for non-broadcast services, so maybe using an async callback or something like that would be great. And more updates, I'm sure, are coming soon. IoT, massive scale, but you need to design everything around IoT. The authentication just doesn't suit us, and it was just a blocker at the time. What about the future? Well, remove the non-serverless part. Let's replace this probably with AWS IoT, but unfortunately it's just not high up on our priority list at the moment because this is just working so well. So AWS will be ready to provide serverless WebSockets at the zone scale. It's just a matter of when. but AWS is already ready to provide serverless WebSockets at most people's scale. And I would highly recommend doing it because your user experience will be so much better. I think I've hit time perfectly. Thank you. If you want to read more about this, then there's a blog post link there on bit.ly for DAZN Pubby. And you can also read more about the failover strategies as well in the links in that post. Thank you.
Thank you, Simon. So I guess if you guys have any questions, please put it into the Q&A into the Hoover app right now, so I can pick it up. There is a comment, not so much a question, from Brian. Strongly approve of the use of plant UML. Nice. And I guess Simon, I do have maybe I guess have you, so with Appsync caching, you could flush the cache, but you can't invalidate a single item, which is a bit annoying. Okay.
Yeah.
Question here. Have you looked outside of AWS, and if so, what things did you consider?
So we did some looking around, not a huge amount though, but when I was looking at building Pubby and whether it was going to be cost effective, looked at alternatives like Pusher, which is a fully managed service that solves everything that we would have wanted. It can deal with our scale, it can deal with absolutely everything we want. But unfortunately, the cost estimations on that were prohibitively high. So we thought, okay, maybe it's worth building something just specific for us. Didn't really look at other cloud providers too much, but from Googling around, didn't see anything that was shining out at the time either.
Okay. And I guess maybe I've got a couple of questions as well, just in terms of how long did you guys take to build this, and how big was the team, so that people get a sense of the actual investment into you guys put into building this the feature.
Yeah, so the feature itself was reasonably simple, as in key moments, being able to subscribe to a live feed of data and work out which ones were important. This WebSockets part, we spent longer actually investigating Appsync than we did building Pubby in the end. Pubby started off as a really simple proof of concept that I had around the Christmas break of, I think, 2018. And I went off and built that over 2 weeks and just went, will it work? And then did a simple load test without all of the functionality there. And it moved on, and I think it was live by mid-January, ready for like the huge load tests that we were doing. So it was pretty small investment, but some of the learnings which you'll see in the blog post took a while to find out. So there are some really horrible things in AWS that took a lot of time for us, like the latency failovers, like gracefully shutting down WebSockets. It's just not nice on AWS because you have to use the draining timeouts in your task, and you want to make sure that when you're scaling down, you don't just kick everyone off and then they cause a thundering herd of reconnections because they still want to be connected. So there's a lot of learning after release that became the investment, but the rate of change now is actually really low. So it's not really being like actively maintained more than keeping dependencies up to date and a few minor features here and there.
Okay, and what about in terms of actual usage? Because you talked about it being potentially the one WebSocket for the whole app. Has it got much further than that in terms of adoption in the company?
Yeah, so it took a while to kind of kick off on that. It kind of stuck with the key moments use case for a while, but it's since been expanded for, so what we have a new feature coming out that's basically showing our real videos to users who aren't logged in. So as part of like a sales process, I guess, you can see what content we have and you can maybe watch some of the live content before you sign up. One of the issues with that is, of course, if we have millions of people then watching the free content and that causes a performance degradation for our real paid users, we need to kick them off and we need to do it quick. So what we do is that we actually have a service running on Pubby that says if the user receives a like red notification on this free to view thing, it will just stop the video immediately. And of course, they don't have to be polling for that. So there's none of the performance impact and they're already getting key moments over it. So it's been expanded for that. And we've also been very recently looking at expanding it for updating our content as it changes. So when a match turns live, we can update the live rail straight away. So it's growing, but it's taken a while to start really moving there.